So we're going to do something that we did back when we were trying to take derivatives of things that acted like this. There was a problem I gave you a while back where it was x to the x. And we used implicit differentiation in class to find the derivative of this. And I said, this is a very weird function. We've never seen this before. The variable is in the base and the exponent at the same time. So it's not a power function. It's not an exponential function. It's some weird combination of both. And what we did, and remember what we did? We took natural log of both sides. And that allowed us to pop the x out and then use implicit differentiation. That's what we did. You go back in your notes, watch the video, whatever. Same sort of thing here. We really don't like the x up here, so we'd like to drop it out. But we can't drop it out unless we have a natural log. So what we do to start the problem is I just call this thing that we're trying to figure out, this limit, I'm just going to call it y. All right? I'm going to create an equation out of this. So remember, at the end of the problem, what I want to know is what y is, right? What's y? That. Right? Okay. Now, I will take natural log of both sides of this equation. The natural log of y equals the natural log of the limit as x goes to infinity of 1 plus 1 over x raised to the x. Agreed? That's natural log of both sides. Then, back in, see if I can go back to this easily. I believe it was chapter 1. Limits. Perfect. Limits, 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 limits. There we go. Okay, there were the limit laws from chapter 1, section 4, when we first started talking about limits. And there was one down here, this rule right here, that said that if you take, oh wait, hold on. Dang it, where is it? Hold on a second. The law, I don't see the law on there. The power one, natural, I don't see it. Interesting. I'm going to have to look that up. I thought it was in the limit laws. We'll put a little asterisk on that. I thought it was in the limit laws, but please take it on faith because I know it's correct. All right, so it's just not in there. All right, here's the thing. If you have a natural log of a limit, are you allowed to pass the limit through the natural log? That's the question. What I thought was on there showed that, but it's what this one shows is that if you have the limit of a function to a power, you can pass the limit in there, find the limit of the function, and then take the power at the end. I was hoping one of those said natural log, but it doesn't. But there is a limit law that says that you can do it with natural log. Now, for those of you who actually are like math majors, because I know that some of you are math majors, that's why you go back and you prove all these things. Because all these limit laws have to be proven rigorously. And that's one of the limit laws, that you can pass a natural log through the limit. All right, so you okay to take it on faith for now? Is that okay? I hate saying that to people, but. All right, so I'm allowed to, because of the limit laws, take this natural log, pass it through the limit, and then that moves the limit to the outside and allows the natural log to sit in front of this big ugly thing. That way I can drop the x out. But the limit law tells us that. And you have to believe the limit law because it's been proven, all right? It's been proven using rigorous, what we call delta epsilon proofs, which is the way that we do proper mathematical rigor, is using what are called delta epsilon proofs. So it's been proven that this is okay. And now we drop the x out. But keep in mind we have an equation here, right? Natural log y equals limit x goes to infinity. The x pops out in front of the natural log. Yes? Keep the equation going, okay? Keep the equation going. What about that? Where does this go? Infinity. Times, I've created a product, haven't I? Okay, 1 over infinity goes to 0. 1 plus 0 is 1. That's heading to 1. Natural log of 1 is 0. Right? Again, you have to go back to the graph of natural log. The x-intercept happens at 1. So natural log of 1 is 0. So this is headed towards what? 0. And we get the indeterminate form that we do know how to handle, right? We know how to handle this. So I just have to pick one of those and drop it to the bottom, right? You see how this is kind of building on itself a little bit? Like we first start off, make sure we can handle all this. Then we're doing this. So we force one down and we turn it into that. And now this form, it looks like we do some natural log stuff to get it to look like that so that we can get it back to that. All right, let's do it. I'm gonna drop x down. I sure as hell don't want to bring that natural log down because that's pretty ugly, right? Okay, so x is going to infinity of the natural log of 1 plus 1 over x over, I dropped x down, so 1 over x. All right, we're gonna move around table. Let's see. Back table in the middle. Who wants to give me the derivative of the top? Because I'm doing L'Hopital now, right? This is infinity. No, it's 0 over 0, actually, if you try it. Okay, so what's derivative of the top? 1 over whatever's inside it. That's what's inside it. 1 over what's inside times derivative of what's inside, which is derivative of 1 is 0 plus derivative of 1 over x. Negative 1 over x squared, right? Because I told you got to remember that one. All over derivative of the bottom, which again, negative 1 over x squared. And they cancel. Nice. Now let x go to infinity. You get what? 1 over infinity, which is going to go to 0. 1 plus 0 is 1. 1 over 1 is 1. So the right side is what? The right side is, when I let x go to infinity, this thing is approaching what? 1, isn't it? So we get the natural log of y equals 1. But what did we want to solve for? We want to solve for y, not y prime. Remember? Y? So how do I release y from the natural log? Bring in the exponent. I do e. I compose e on both sides, don't I, to release it? And when you do e of natural log y, you get y. And that means the answer is what? E. E. Which is the natural base, isn't it? The natural exponential function, that the base e is the natural base. Any questions? I want to recap what we just said. We just said that e is equal to the limit as x goes to infinity of 1 plus 1 over x to the x. That's what we just said. Right? In fact, some people, because you can define e a lot of different ways, but for a lot of people, that's the definition of e. If you want to know what e is, that's its definition. Now, if you don't believe it, just pick a very big value. If you knew this already, e is approximately 2.718 something, keeps going forever. If you pick a large value of x and plug it in right here, here and here, do it on your calculator, you'll get a number that's close to 2.718. And the bigger your number is, the closer you get. Do you believe me? You'd have to do it yourself, right? So you could plug in, if you plug in 1, what do you get? Let's try 1. 1 over 1 is 1. 1 plus 1 is 2, right? 2 to the, I'm plugging in 1. So 2 to the first power is 2. So if I plug in 1, it's going to, if x is 1, it's going to, this thing's going to spit out 2. Is that close to 2.718? Not really. I mean, it's 2. I guess we're close. Now, if I plug in 2, then it's going to be 1/2. 1 plus 1/2 is 1.5. Raise 1.5 to the second power, and I assure you it's closer to this than 2 was. And if you plug in 3, it's even closer. And if you go to infinity, the larger you get closer and closer to true value of E. In fact, that's the definition of E. That's the precise definition of E. Now, there's alternative ones, but that's a precise one. So since I'm out of time, I'll just share a couple of things with you. Some of the most well-known numbers in mathematics are things like pi, right? Like pi is one of the most common ones. And if someone asks you, what's the definition of pi? You would say 3.14 is what it is, but by its definition, it's the circumference of a circle divided by its diameter. That's the definition of pi. You draw any circle on a two-dimensional flat sheet of paper. If you give me the diameter, the distance all the way across, and if I know the circumference, the distance around, if I take that number, the distance around, divide it by this number, d, I will get pi, always, on any circle. So that's the definition of pi. The problem is, if you know the diameter, like let's say we didn't know what pi was, if you know the diameter, it's very hard to get the circumference. Or if you know the circumference, it's very hard to get the diameter. I mean, imagine trying to draw a circle and measure it. It's difficult to do. So that's the definition of pi. E is now, has a definition. It's the limit, blah, 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 right? What are some other, are there any other interesting numbers in math that you like, that you've heard of? Oh, okay. I thought they said 5. I was like, well, I guess 5 could be interesting, right? So like we're talking golden ratio, right? Okay. That has a definition also. You could get it recursively using the Fibonacci sequence, which I'm not going to write here because we haven't even talked about sequences. And then, let me see, what are some, let's see, what's this one? I? That's pretty important. You've seen it before, right? It's the square root of -1, right? That's that imaginary number. What are some other important numbers in mathematics? Well, how about some of the ones that are less obvious to you that are super important? Something like the number 1. 0, right? These are hugely important numbers in mathematics. We talked, did I talk about in this class that, yes, I did. We were doing the hidden 0, right? We talked about seeing a hidden 1 next to something is a big deal, but seeing a hidden 0 is an even bigger deal. 1 is what we call the multiplicative, I'm just going to put multiplicative identity, and this is the additive identity. So what you don't realize sitting there as Cal 2 students or Cal 1 students, which I didn't realize also when I was at your point, is that the number line has a lot of structure to it. You know, all the numbers that live in there, there's a lot of structure in here. Things as simple as, okay, is there a number in there that when I multiply anything times that number, I get itself? And that's the number 1. It's called the multiplicative identity. There exists something in our number system that when you multiply something by, it doesn't change anything. And there's another one that works for addition. And why is it important to have a number that I can add anything and get back what I started with, or multiply and get the same thing? Because if you have these two things on your two operations, because our numbers only have two operations, right? Multiplication and addition. Because subtraction is addition, isn't it? Subtraction is addition. And division is multiplication of the reciprocal. So there are really only two operations in our number system, aren't there? Those are called binary operations. We have two of them. So if we have two binary operations and we have an identity for each one, That adds structure to our system. And what you need in order to get what we have, our real numbers, in order to get the complete structure, we have to have 12 things be met. There are 12 conditions. And those are called the field axioms, and that's why we called the real numbers a field. Is that the way you spell field? I before E? Except after C, but does that work? Does that work for there? Yes? What does it not work for?
Weird, yeah.
Weird? It doesn't look for weird, or it doesn't work for weird?
Or receipt.
Or receipt? Okay, so why not? It's English, right? Screw English. No. Yeah, that doesn't make any sense. That's why I do math. That's why I do math, right? I before E, except after C? Yeah, right. Is that right? Who cares, right? You understand what I'm saying? That's what's more important, right? Communication. So look, the real numbers form what's called a field, and there are 12 field axioms. 2 of the 12 are that you must have a multiplicative identity and you must have an additive identity. And that makes the number 0 and the number 1 extremely important, all right? So what I'd like to show you now with this number that's really important because we like it, it deals with circles and it's cute, right? And then E we found is fascinating, and E is, that function is the only thing that's its own derivative, and that's fascinating too. This was always like strange, right? Like imaginary number I, it's like, ooh, weird. So we have what is argued to be the most beautiful formula in math. Most beautiful equation in math. Which is that. That's arguably the most beautiful equation in math. People can, you can always argue about beauty is subjective, right? But it's one of those, it's an equation that when you look at it, you're like, wow, that looks kind of weird, right? We know what e to the pi is. That's just e raised to a number, right? But what's e to the I pi, or pi I? Now you have an imaginary number in there, and that makes things kind of weird. But according to what this equation says, this is actually just what? -1, right? Which it is. It is -1, but it's just a fancy way of writing -1. But it is correct. If you take e and raise it to the I pi, you get -1. And so what makes this equation so beautiful is that it brings all these really nice numbers in mathematics together into one place in one true statement. You have the additive identity, you have the multiplicative identity, you have pi, which we like, you have the natural base e, you have the imaginary unit, all together in one place. So anyways, thought I'd show that to you. All right, let's talk about the exam. So if you didn't catch me at the beginning of class, I was saying that your exam, which is on Monday, so you got the weekend to study for, I don't have a review for it, but I found this on in Canvas, under the files for the class. There's somewhere in there, I think it's called, well, it says it up here. It says 2413 Exam 3 Review Fall 14, F14. So that's a review from a year ago, and we were at a different place in that class than we are in this class, so that's why it says Exam 3. All right? We're about to take Exam 2. So here are the things I think you should look at on this review. I'll write this down in case you need to go back and look this up. On the 2413 Exam 3 Review, Fall 14, if you look at problem number 1, these are all derivatives. All of these derivatives involve chain rule, product rule, quotient rule, and involve derivatives of exponential and log functions and inverse trig functions. So it's like all of the things that we've talked about, all in a couple of problems for you to practice. I'm not implying that I would give you a problem on the test that would have 6 derivatives for you to take. This is practice. This truly was a practice set for this class, all right? So I recommend you work through all those. If you can work through all those, you'll be in pretty good shape as far as derivatives are concerned. Number 2 was logarithmic differentiation. So that's definitely something that'll be on our test. Logarithmic differentiation is where you came in and you took log on both sides. So I actually wrote that down a second ago. That problem, we did log on both sides, implicit differentiation. Do not confuse this with limits and L'Hopital's rule, totally different things. So, and then also we did this in class where, like on part D, where if I take log on the left and right hand sides, on the right side I could use the rules of logs to split up, like subtraction and then multiplication, then pull powers out and then take the derivative. So that's what that number 2 is about. All right? Number 3 we have not talked about. All right? Since we haven't talked about it, I'm going to focus mainly on this on the test, okay? So 3 won't be on here, all right? 3 will not be, so don't look at that 3. That's kind of where we're headed. C we haven't talked about. I mean 4 we have not talked about. The mean value theorem. 5 we have not talked about. So you're like, that's not a very good review then, huh? Whoa, why is that going so slow? 6 we haven't talked about. 7 we haven't talked about. But 8, I believe, is all L'Hopital. Yes. I would say give them all a shot. At least A through E. A through E are all going to give you 0 over 0 or infinity or infinity forms. At F, you're going to get, oh, I did that one in class. Yep. You're going to get a form of infinity times 0. Here's another one. I did something very similar to that in class. On this one, H, I'll just give you a hint on that one. Get a common denominator first. Put them together, common denominator, and then do what you need to do. On I and for K, I would probably put something like that on your test as a bonus, because that's kind of like how I just showed what E was, right? It was 1 plus 1 over x to the x, and I had to do natural log both sides. That's kind of the last thing I've talked about today, so I'm not going to put that on the test. So I and J, look at those if you want for bonus. We good? This isn't everything though, all right? Because there's still in here what? Related rates. So related rates would be the other topic that's on this test. And did I have a review on there that had any related rates?
I found the actual exam number 2 for spring.
Okay. Yeah, let's take a look. I don't know how many of you have actually taken the time to go through all the stuff I have on this website. There's a lot of information here. By the way, the answers to all of these are on the web too. Every one of those review problems, or every one of those.
You had some course notes that looks like you did on a computer.
Yes.
On there, and those were really good for related rates.
Yeah. Let me see. Class files. So if I go into files and I go to old exams, where is it? Exam review solutions. Is it in here? Exam review fall 2014, right there. So it's like buried within a couple of folders. And then if you want the answers to that review, I believe it's called Exam 3 Study Group. And that is, I think, a 20-page document of the solutions to that. All right? And if you go to YouTube, let's see. If you go to my channel on YouTube and go to the playlist, see if I have my Cal 1 from last spring or fall. I don't remember. See if I have the study group video here. Oh, there it is, study group. I don't know if y'all caught that. I went to the fall 2014. If you click on this study group video, It's a 3-hour video of me doing that entire review. I was with students that met me, I think, on a Saturday, and I worked with them for 3 hours. We got through most of it. But remember, on the review, there's only, oh, number 8. Sorry, number 8's on there too. On the review, that review I'm talking about, there's only 3 of those problems that you're going to be concerned with, right? All right, so let me,
Long video.
uh-oh.
It's a long video.
It was a long day.
Did y'all take a break?
I think we did. I brought tacos, I think. Yeah, I took tacos. We ate, we drank, soda and stuff. Okay, so what else is in here? Someone else said they found an old exam, so let me go back to exam 2. See, this exam 2, I don't think that, let me see what's on here. I don't think that this one is really that applicable. What's going on here? Oh, you know what? I know what's going on. Try it again. Old exams, exam 3 study group. So that there's that PDF. I think it's in several places. Exam 2 review. Let's see what this is. Equation of tangent line. That's not going to be on this exam. We already did that. Use the limit definition to find the derivative. We're past that. We're past all this. We're past all that. Here's a couple of problems with like product rule and quotient rule, but I would say maybe 15. That's chain rule. This is chain rule. This is chain rule. This is product rule. Oh, yeah, there is some stuff on here. Implicit differentiation. That's another topic that's going to be on this test. Implicit. Remember where you can't solve for y, so you have to take the derivative on both sides of the equation implicitly. So if you look back on this one, it starts on number 21. So I'm looking at the exam. It says 2413 exam 2 review. Number 21, 22, 23, 24. Those are all implicit differentiation. And then the review, the solutions for that are up there also. So you've got it all there. And then, what was that thing? It said complete exam solutions, spring 2015. So I actually put up all my exams and all the answers for all the exams I did in the spring. This is the one you were talking about, right? Mm-hmm. Yeah. So if you get to exam 2, where does exam 2 start? There it is. There's my exam 2. So that doesn't have, you find the equation tangent line. That's not for you. It'll pick up whenever we get to like implicit differentiation, if it happens. What's that? That's a little quotient rule. Chain with product. Chain. This one, oh man, that problem got everyone. Everyone had so many problems with that constant, with those constants. There was a product rule right there. And I'll let you mess with that.
If we were doing that, like, wouldn't it be what if it was like, because we were doing one of those homework problems for the one that was the A, B, and constant.
So 41.
Yeah.
And like alpha and beta.
Yeah.
And we would treat those as like constants.
Like numbers.
Yeah, so we wouldn't take the derivative of them.
Yeah, if you ever have a problem where, can you kill the lights over there for me? If you ever have a problem where, let's kill a little more, please. One more, yeah. Yeah, I don't know if I'm going to pick this up on the camera. if you ever have a problem where it's got these alpha beta things in there and you're getting confused, just replace them with numbers and try the problem with just the numbers and see how things work out. And then go back and look at what would it be alpha beta, because it's the same principle, just with letters instead. Does that make sense what I'm saying? Yeah. Okay, so looking at this exam 2 from spring 2015, number 9, that's an implicit differentiation problem. That's definitely a good one to look at. Find the slope of the tangent line. That's a fair one too, because this is an implicit differentiation problem. To find y prime, and then once you find y prime, you plug in the point, and you get the slope of the line. Another implicit differentiation problem, asked to find y double prime. If you did your homework, you know that sometimes that can be messy, because the original function appears in the derivative, and you have to replace it in there. Okay, here we go. This is what I want to get to. Related rate problem. Conical cup. We did one of those in class, didn't we? I happened to give them this on a test. That was the only one? What do we have here? This is a derivative, trying to find derivative, but using properties of logs first. This is a logarithmic differentiation. Take log on both sides. Notice you have x raised to the 4x. X appears in both places, so you bring in the log. Another related rate problem. Man walks, this was a bonus though. Man walks north, not because it was harder, it was just the time considerations. And exam 3, so, all right.
And then your written out notes on related rates is really good too.
The notes, class notes, or the handwritten notes?
Handwritten notes.
Is that in here?
I think so. If you just go to related rates, there's 2 parts, yeah.
Yeah, so there's a bunch. I have some things in here from related rates from lectures that I did in a face-to-face class. There are actually videos that go with these. So if you go to YouTube and you find, I believe this was probably fall or spring, if you find my day 13 related rates, you would actually see a video of me doing all of these related rate problems. Spheres. Anything else? I'm not trying to ruin your weekend. I'm just trying to show you what's out here for you, okay? I don't want you getting overwhelmed with information. Let's see. Another sphere. Okay, here's a good one. Plane flying overhead. That's a good plane. Let's see. Pole. We did this one. Cone. So, I mean, a lot of these are things you already saw. Okay. Any questions on the exam? What are we going to use? You can bring your formula sheets, right?
Any questions?
Meaning, I don't know. I haven't made the test. So I don't want you to look at any of these and be like, okay, that's what it's going to look like. It's, you know, this is more, especially because this is our second exam. I mean, you just got to be prepared for the material. Question-wise, I don't know. Most likely on the related rates, I'll probably give you, you know, here are 2 problems, choose one or something. Or here are 3, choose 2. It'll depend on how the rest of the test works out. You know, time will be an issue because we know the related rate problems can be time-consuming. So you'll want to maybe knock everything else out and then tackle the related rates at the end. So we clear on what's on the test? Chain rule, implicit differentiation. Sorry, you're ready to go. Chain rule, implicit differentiation, related rates, derivatives of logs, exponents, inverse trig, and then L'Hopital. But just some of the L'Hopital, not all of it. All right, everybody, have a good weekend.